Hello, everybody. We are in the home stretch. We are in the last four questions of the exam paper. So 45 is what we're going to start with. Which of the following equations has at least one real solution? So I remember this from a couple years ago. This was a very oddly placed question. I don't know why it's towards the end of the exam. It doesn't make any sense because it's not really a calculus question. This is more of a pre-calc stuff, but whatever. It's been jammed here, so be it. All right. So we just have to say, well, which of these could actually happen? So take, for example, 2 to the x. Well, 2 to the x, and you might remember its graph, is always above the x-axis. It's never going to be equal to -5. So that one's out right away. Okay. Other things we might think about, considering the graph, how about arctan? Graph of arctan looks like this. It's always between pi by 2 and -pi by 2. In fact, it's strictly between them. It never actually hits them. They're horizontal asymptotes. You might remember pi is about 3.14. Divided by 2, pi is definitely less than 4, so pi by 2 is definitely less than 4 by 2. So this is definitely way less than 2. You're never going to hit 5. 5 would be way up here. The function never even approaches it. So D is also out. For the same reason, sine cannot be 5. I'll draw a little quick sketch there. But sine always bounces between 1 and drawing the arctan one again. Sine always bounces between 1 and -1. So sine would never even be 2, let alone 5. Okay? Now you might say, well, secant. Surely secant could be 1 over 5. But no, secant is 1 over cosine. Remember what cosine looks like. It bounces between 1 and -1. Secant being 1 over cosine will actually have its lowest value be 1, and it's got nice asymptotes there. So it's always bigger than 1 or less than -1. It can't ever be something like 1/5. So that would tell me that surely tan equals 5 must be the answer, right? So let's go up a little bit. So could tan possibly be equal to 5? And think about the tan graph. It's got asymptotes as well, but tan actually goes all the way between -infinity and +infinity. So yeah, it crosses the line y equals 5. It intersects 5 at some point. So that's got to be our answer. Okay. All right, 46. I think the last three are just volumes. Yeah, volume, solid or revolution, and then one of these fun shaped base questions. Those are always such a pleasure to do, where they give you the cross sections rather than ensure that they are disks. But we will get to that. 46. Determine the volume of the solid or revolution obtained by rotating the region bound by y equals x squared and y equals x cubed about the x-axis. I think we've even done this one in class. Let's draw a quick sketch. So that's x squared. X cubed will actually be a little less than that. So we want sort of this area here. Now, you can, of course, say, well, what's the point of intersection of these? And you'll get x is equal to 0 and 1. But we've done these so many times, you might already know it's 0 and 1. And in a multiple choice question, no one cares, and this exam has been just multiple choice, but try and show your work for points of intersection if there are written questions and that sort of a thing. So we're going to integrate from 0 to 1. Which one's the bigger? We're rotating around the x-axis, so the one that's further away from the axis is x squared, so the outer radius is x squared. So we'll do x squared squared, and then x cubed squared. So do pi. And we want to integrate from 0 to 1, x to the 4 minus x to the 6 dx. And so we will get x to the 5 over 5 minus x to the 7 over 7. We're going to go from 0 to 1. So that'll be pi 1/5 minus 1/7 minus 0/5 minus 0/7. 1/5 minus 1/7, that'll be 7/35 minus 5/35. And so that'll be 2/35 times pi, and that is e. Okay, another solid revolution question, even less space. I may have to go down to the blank sheets. We will see. Which of the following integrals represents... Oh, no, so this is sort of a reverse question. It represents the volume of the solid revolution obtained by rotating the region bound by x equals cos y, and x equals 0 from y equals 0 to y equals pi by 2 about the x-axis. Now, we didn't do any rotation around the... Or sorry, not the x-axis, the y-axis. We didn't do rotation around the y-axis specifically in class, but it's going to work the exact same way as always, especially because, well, our function is x in terms of y. If you were really upset by this, change it so it's y in terms... so all the x's become y's and all the y's become 0. So y equals 0 would be the x-axis, x equals 0 would be the y-axis. So you can absolutely just answer this question in terms of x's and then switch it all back to y's. Part of why I never really bothered doing one of these in class. Okay. So cosine, it's at 1 at 0, and then it's at 0 at pi by 2. Okay. And we are furthest from the axis we are rotating around when we are cosine. So that's going to be our... yeah, I don't know why. They're just trying to be sneaky. The y-axis is x equals 0, or in this case, the x-axis is y equals 0. So we don't have an inner and outer radius. Our radius is just cosine. So it'll be cosine squared. They're going to do it in terms of y. So we'll have cosine squared y from 0 to pi by 2. And we're going to have a pi kicking around, which happens to be this pi right here. So I guess A is our answer. I didn't mean for it to be... I just noticed that that's the only one that really has a cosine squared. I guess this one does, and so does this one. But they also have other things that we don't need to get involved with. They have an inner and outer radii, I guess, which is just not the case for this one. Now, if you're upset by this, you know, you're more than welcome to draw the picture of x equals cosine y, which is going to look a little something like this. And basically, you're just doing everything but with the page shifted the other way. The line x equals 0 is right here, so we're being bound by this particular curve. And we're going from y equals 0 up to y equals pi by 2. So, other than that, everything's fine. We're still... What's the distance to your axis? Well, it's cosine y. Okay, so we get our answer of A. No sweat there. Alright. 48. A solid S has a base in the shape of a circular disc of radius A, hurrah, and parallel cross-sections of S perpendicular to the base. Okay, so these will be the cross-sections that we need to find the area of. And these are going to be equilateral triangles. So we'll get a very small one here. Equilateral triangles, equilateral triangles. And then they're going to get smaller as the circle sort of closes in on itself. Okay. So these are equilateral triangles, and they're sticking straight up off of my circle. Now, if we looked at it from the top-down view, we'd have our circle, and we know the radius is A. So I might create an imaginary x-axis going from minus A up to A. And then based on where we are between minus A and A, we get these cuts across. So looking down, our equilateral triangles are going to be flat. So they're just going to look like lines. They're going to give us the base. And then, well, they're equilateral triangles, so if you know one side length, you know all the side lengths. So in terms of x, what are these bases for these equilateral triangles? Okay. Well, we can use a trick we've seen a couple times, most notably when we did an optimization question involving that cylinder inside a sphere. But we can connect up the radius. We know the radius is A here. A nice little right angle here. And what is this distance here? Well, it's going to be x. Okay? X is going to be well, technically it'll be absolute value of x. But we'll see that that'll go away in a moment because we'll be squaring things. But we're measuring from 0, which happens to be the center. Okay? And so the base of our equilateral triangle is going to be twice this length. So the base, or the side length, is going to be twice. And then what is that length? Well, it's square root of, we've got a nice little right angle triangle here, a squared minus absolute value of x squared. Absolute value of x squared is just x squared. So we'll get 2 root a squared minus x squared. So that's the base of our equilateral triangle. Great. And so, well, we know a side line. We do what? We know my range of x values, so I know I'm going to integrate from minus a to a, but I need the area of these cross sections in terms of this x. And all I've done is figure out the base. Okay. Now you might remember, because I've sort of tried to get this in your head a couple times, that we do need geometry formulas other than just, length times width times height is a cube and pi r squared for circles. And I've mentioned equilateral triangles because I remember in class, because I remember this one coming up, and I've used equilateral triangles over the summer to bring marks down when they were too high and that sort of a thing. It's not a geometric formula people are familiar with, so it causes a little bit of confusion or a little bit of thought has to go into getting the answer. And so either you remember it, or you can work it out. Equilateral triangles, 60 degrees. And so if we drop a little altitude, a little height, because we need base times height, we could get a nice little 30, 60, 90 triangle, one of those 2 to 1 to root 3 style triangles. Okay. And so you can actually figure out that if my side length is, say, s, then the base here will be s over 2, and so the height will be root 3 times that base, so root 3s over 2. Okay, and now the base is s, and then so we do 1/2 base times height, and so in terms of the side length, the formula for an equilateral triangle is root 3s squared over 4. Okay. Well, I know the base side length for my cross section based in terms of x. So the area of x here will be root 3, and now it's 2 root a squared minus x squared all squared over 4. Alright, so that's root 3, 2 squared is 4, that'll cancel out with the 4 on the bottom, and then the square and the square root will cancel out, we'll get a squared minus x squared. So when all is said and done, the area of these individual equilateral triangle slices is root 3 a squared minus x squared. And now this is the thing that I want to integrate. And I earlier chose the bounds, or the range of values of x here, so minus a up to a. It's a common one with circles. You want to put the center of the circle right at 0. That's sort of the idea. So integrate that. We'll get minus a to a, root 3 a squared minus x squared. Now, some of that's constants. So let's separate these. Root 3 a squared, and then root 3 x squared. We'll have to do different things to each one. So one of them's a constant, so we'll just get root 3 a squared x, going from minus a to a. And then minus root 3, and that'll go x cubed over 3 minus a to a. Okay, so that'll be root 3a cubed minus, and then the minus a going in will turn it into minus root 3a cubed. So we'll get 2 root 3a cubed from this first little bit. Minus, now we get, well, the root 3 and the 3 will cancel each other out in a little bit. So I could turn it into 1 over root 3. So we get a cubed over root 3. Minus, and then negative a cubed will also be minus a cubed over root 3. So I guess those would turn into a plus. So it'll be minus, turn this into a plus, minus 2a cubed over root 3. We could take out a factor of a cubed. So 2 root 3 minus 2 over root 3. A cubed, and now that I've got a single answer, does that actually look like anything that we've got? Now, they have a bunch of pies in here. Oh, no, there are a couple that don't have pies. Oh, for a moment I was a little worried there that I'd misread it and it was solid revolution or something. So B and A are right out, just because they've got pies in them. But C and D, they both have A cubes in them. Let's get a common denominator of, let's say, 3. So that'll be 6 root 3 over 3. minus 2 root 3 over 3. And so that would be 4 root 3 over 3, a cubed, and I think that's d. Let's double check. Yes, indeed it is. And there we go. We're all done. Our 2016 final. It's been a heck of a paper. And those are the last 4. And again, if you've missed one, missed a particular question, you want to go back and retry it, you can take a look and find them in groups of 4s. But we're all done, so the only thing left for me to say is good luck on your remaining exams, including your calculus final.